Right then, Mei M2 January 2011, question 2. A mixture of things in this question. There's mainly momentum to start with, and then some energy and power for the second bit. Obviously MEI questions are longer than some of the other exam boards. So let's show you the full question. There it is. If you'd like to pause the video and have a good read of it, and then continue when you're ready. Okay, so the first part is conservation of momentum. We've got a firework, and the firework is of total mass 0.064. Put that in on here. 0.064. That's the firework before it explodes. And the kinetic energy, the total kinetic energy given to B and C is 0.8 joules. So total K is 0.8. And we've got all the information we need there. By considering both kinetic energy and linear momentum, calculate the velocities of B and C after the collision. Well, first of all, using the principle of conservation of linear momentum, we've got naught equals 0.004 V1 minus 0.06 V2. Naught being the momentum just before it explodes, because it was instantaneously at rest. And that simplifies to V1 minus 15 V2 equals 0. Now the KE, half mv squared then, so 0.002 V1 squared plus 0.03 V2 squared equals 0.8 joules. That tidies up to V1 squared plus 15 V2 squared equals 400. Now V1 is 15 V2. So from this equation, we can get 15 V2 all squared plus 15 V2 squared equals 400. Okay, that gives us, when you tidy that up, 240 V squared is 400. Giving V2 equal to 1.29. Now V1 is 15 V2, so that gives us 19.4. Obviously these are both meters per second. Right, that's that part. To save coming back to it, let's just quickly look at there was 8 marks for that, so I'm quite generous. Let's just look at where the marks were allocated there. There was an M1A1 for the principle of conservation of linear momentum, and likewise for the kinetic energy equation. So half the marks were those 4 there. There was an M1 for solving the kinetic energy equation with for solving both equations. And then there was a total of 3 accuracy marks as you work through the stages in this question. I'll just put it as A3 because it's not important exactly what lines you put them against. But that's how the 8 marks were shared out. 1, 2, 3, 4, 5. Yeah, that's right. That's 8. On to the next part then. For the next part of the question, something totally different. We've got a car going up a hill. I've shown S here as a resistance force that we don't know. But what we do know is that the car goes up a vertical height of 20 meters and its speed decreases. So we've got a loss of kinetic energy and a gain of gravitational potential energy. And if the road was smooth, the hill was smooth, we'd have loss of KE, would be accounted for by the gain in GPE. But because there's resistance, there'll be another term here which is work done against resistance. In other words, the kinetic energy loss partly goes to gaining gravitational potential and partly is lost as work done against the resistance. So all we have to do now is work out these expressions. So the loss of KE is a half m, which is 400, times, it'll be 30 squared minus 12 squared to give us a positive quantity. That's the KE that's been lost. That's equal to 800 mgh, 800 times 9.8 times 20, vertical height, plus we'll just call it WD, because that's what we want to find. Right, calculate your time, plug in the numbers, and WD works out to be 145600. And that'll be joules. Oops, just write that again, went a bit crooked, joules. Okay, that's 4 marks, and the 4 marks were basically a method mark for the principle of conservation of energy, and then 3 other accuracy marks. Let me just see if they were anywhere specific. No, it's not clear exactly what the accuracy marks were. I think there was 1 mark for the MGH, and a bit unclear about that. 1, 2, and then 2 other accuracy marks, A2. And now there's 1 more bit of the question left for 5 marks. And for this part, the car is, we're doing this bit now, where it says, in another situation. The car's going at constant speed up a slope, climbs a vertical height of 20 meters in 25 seconds. Right, so that they've told us the time, and we know the resistance to motion. So I've drawn a diagram up here. We know it's going at 18 meters per second. We know it's going at 18 meters per second, and we know it's been going for 25 seconds. So that tells us, before we do anything else, that's what I've done here. That tells us the distance it's gone along the slope is 18 times 25, 450. So we know the angle. Specifically, we know the sine of the angle, 20 over 450. Right. We've got to find the power of the driving force required. Well, remember P equals FV. So if it's going at 18 meters per second, it'll be F times 18. So we're nearly there, we just need to find F. Now how can we find F? Well, since it's going at constant speed, then there's no acceleration up the slope. So resolving along the slope, resolving up the plane, or up the slope, whatever you want to call it, we've got F minus 750 minus 800g sine alpha equals 0. In other words, F equals 750 plus 800g times 2 over 45. Alright, work out F then and work out P from FV, and that'll give you P equals 19772. That's a 2. Every time I get to the bottom corner of this graphics tablet, 19772 watts. It always goes funny in the bottom corner of the pen. 19772 watts then is the power. That's doing P equals F times V. Using the F calculated from this with the V of 18. For this part of the question there was 5 marks, 2 method marks, 3 accuracy marks. So the method marks were for the resolving equation. I need to do this in red so it show it up. So there's a method mark there and a method mark for the P equals FV. There was a mark for the sine alpha, and then there was 2 accuracy marks. Yeah. So 1, 2, 3, 4, 5, that's right. Okay, that was Jan 11, question 2. I hope that was helpful.